back to another session of FEA using SolidWorks. In the previous session, we took a look at the UI in the SolidWorks software and also how to migrate from 3D modeling environment and also how to migrate from the 3D modeling environment and into the simulation environment. In this video, we will be discussing how to perform linear and non-linear static analysis. We will also be discussing how to perform a dynamic analysis. Along with this, we will be discussing how to perform FEA analysis using 2D simplification. So let's begin. Let's first create a model. A simple plate with a hole is a basic problem that any FEA engineer would start with while learning the software. So once I show you how to add initial parameters, we'll proceed to the analysis. So here I've opened the SolidWorks window. I will click on New and select Part and click OK. As you can see, the software was opened into the part modeling interface. So our course of action here would be to create a simple plate. To do that, let's go to Sketch and click on the sketch icon. This will give us the three different planes. I'll select the top plane and it is changed on to top plane. Here I'll just select on the rectangle option, but instead of corner rectangle, I'll be selecting center rectangle. I'll select the mid plane and create a rectangle. Now using the smart dimensions, I'll set 50 millimeter as dimensions on both sides. So let's select this one and change it to 50 here. And the dimension on this side also will make it as 50. Okay, we have our plate and let's click on the tick. Our next course of action would be to create a circle. So let's go to the circle option and select it. Now let's move to the midpoint here and create a circle. And we want our circle's diameter to be around 15 millimeters. Here, if you notice, it is actually radius and not diameter. To do that, you can either make it as 7.5 or you can go to smart dimensions directly and select it from here. And here we'll change it to 15 and it has become 15. Let's click OK. Now let's go to features and extrude this. Here let's give an extrude thickness of 5 millimeters. I'll just click on 5 and click OK. Okay, so we have our plate. Now our work will be to perform a simple static analysis. To do that, we need to go to the simulation module, but as you can see, it is missing here. As I've just shown you in the previous video, we just go to SolidWorks add-ins and click on the SolidWorks simulation icon here. This will activate the license. What the software will do is will check in the licensing server and see whether we have bought the SolidWorks simulation, and if at all we have bought it, it will show it. If it is not here, it won't come. So let's go ahead and click on simulation and click on new study. Since we're doing a static study, we'll select this one. It is actually selected by default, so no need to select it. I'll change it to static plate and click OK. Now the left side design tree has changed into the simulation design tree. Our first work would be to assign a material to this model. To do this, right click on part 1 and select apply or edit material. Here we have a list of all the materials which the software took from the database of SolidWorks. Here we'll be selecting the default alloy steel, and here you can see all the different properties of alloy steel are mentioned, like elastic modulus, Poisson's ratio, shear modulus, mass density, tensile strength, compressive strength, and many more. Let's hit on apply and let's press close. Our next work would be to give fixtures here. Let's go ahead and press on fix geometry and we'll fix this side and press OK. Now I'll be selecting Control 7. Next we'll be giving the external loads. To do that, let's go to force. This is done by right clicking on external loads Let's go to force. Here we need to select the phase in which we want our force to be acting. Since we are looking forward for a tensile force, I'll select on this side. And now I'll be reversing the direction by clicking on this checkbox. If we don't reverse the direction, the force will be acting inwards. That's not what we want. We want a tensile. If it acts inwards, it will be a compressive. If it acts outward, it is tensile. So I'll just reverse the direction and I'll give 1000 newtons of force. And I'll press OK. Now our next work would be to mesh the model. So to do that, let's right click and select create mesh. We'll give the default mesh here and select OK. Okay, so we have our meshed model. This is a very simple analysis, so we're not giving much emphasis on the quality of the mesh or what type of mesh we are using. Let's press on run the study to run our study. As I said, it is done. Here you can see that we have got quite a colorful model as result, and the deformation is also very high. The high deformation is due to the deformation scale, which we can see in the top left corner. We have already talked about this in our previous video. The different stress values in the legend correspond to the different colors in the model. At the bottom, we can also see the yield strength value of the metal. And we will also notice that the stress value in the models are well below the yield strength value. Since all stresses are within the linear region of the stress strain graph, this analysis has given us acceptable results. Now you can also notice that the stresses right now are in the order of 7, 6 and 5. I will be increasing the force by a factor of 10. To increase the force, we can just right click on the external loads and click on the edit definition option. Here let's add another 0. So this becomes 10,000 newtons or 10 kilonewtons, and let's press OK. Since we've changed the input parameters, you can see that there is a small yellow icon that appears next to the results option. That means that some changes have been made to the parameters of the model. So we'll be running the study again. Let's click on run the study. Okay, so we've got our result. Now you can see that all the stress values have also increased by a factor of 10. But even now, the stress values are within the yield limit. Now let's increase the force by another factor of 10 and let's run the simulation again. Again, I'm going to be doing the same thing here. I'll just go to the force value which we have inputted, right click on it and select edit definition. Since it is now 10,000 newtons, I'll make it 100,000 newton or 100 kilonewton. I'll press OK and run the study. And we have our result, but this time you'll be able to see that there is an extra arrow mark in the legend here. So what happened here? So what happened here is that since we are using a linear analysis, the results are valid up to the yield point of the material. The arrow mark shows the point at which the yield strength of the material was exceeded, and thus all the results above the mark are not acceptable. We will have to run a nonlinear analysis to get realistic values from the simulation. So since we are performing a static linear analysis and the stress values which we had yielded are much higher than the yield strength value, then we should be switching to a nonlinear analysis to get reliable results. So let's do the same. Let's run a nonlinear analysis here. To do that, right click on the static plate name here and select create new simulation study. So to create a new study, we'll go to static plate and select the option copy study. Here under the target study, we'll select nonlinear and we'll select OK. Now let's run the analysis. Here, when we run the simulation, you can notice that the solver is taking much more time to compute this compared to the linear static analysis. And now we have the correct values for the stress. Here you can notice that the stress values in the nonlinear analysis are much lower than the linear analysis. To understand this much better, let's take a look at the stress strain plot of a metal. Now that we have the stress strain graph of a metal in front of us, here you can notice that the value increases linearly in the initial phases and then it decreases, and the rate of increment reduces after a certain period of time. And this is what is happening in the nonlinear analysis. As the amount of force that is acting on this phase increases, the total amount of stress that is developed in the metal also increases. Once the stress value crosses the yield strength, the rate at which the stress value increases starts to fall down. That's why you'll see that the stress values in nonlinear analysis are much lower than the ones in linear analysis. Now that we have a fair understanding between the linear and nonlinear FEA analysis, let's consider another example. Here we will first run a static analysis on a beam and then increase the load to check what happens when nonlinearity occurs. Okay, so I have the new window here. So what I'll be doing is I'll be making a cantilever beam. So let me go to features. I'll be selecting sketch. We need the right plane here. So let me select the right plane. And using the centered rectangle option, I'll make a rectangle. Now the dimensions will be 50 millimeters versus 50 millimeters. It will be a square of 50 millimeters. So I'll change it to 50 here and 50 here. Now next we'll be extruding it. We can directly press extrude, and I'll extrude it to a distance of 1000 millimeters or 1 meter, and let's press OK. Control 7. Okay, so this is the total length of our cantilever beam. Let's go to simulation, new study, and we'll be doing a static analysis. So I'll name it a static beam and I'll press OK. We'll be doing much similar things that we did for the plate. So I'll just give a material to it. I'll give apply or edit material. Select alloy steel, apply, the color changed. Let's close it. We'll be fixing it. Let's go to fixed geometry. Since for a cantilever beam, one face is always fixed. I'll fix this face and I'll press OK. Now we'll be giving it external loads. Let's go to force. So what we want to do here is we'll be giving 500 newtons of force on this edge, and you can notice that the direction of force is actually in this direction, so that is not our desired one. So to do that, we'll give selected direction and we'll select on this face and we'll reverse the direction. So what we've effectively done is we've selected the edge here, we selected the face at which we want force to be acting in this place, and we selected the direction or the plane along which we want our force to be applied, and then we reversed it. Now I'll input the amount of force, that is 500 Newton, and I'll press OK. Now we will go ahead and mesh the model. Let's go to mesh, right click and hit mesh and run. Since this is a very simple model, we don't really need to worry ourselves with the intricacies of meshing. So I'll just select mesh and run. Okay, so we have a cantilever beam with a little bit of deflection here. Now I'll be increasing the amount of load by another factor of 100. So I'll go to force, right click, edit definition, and let's make it 50,000 newtons or 50 kilonewton. Let's press OK and let's run this study now. Okay, so we have an error here. So what has happened here is that the software has detected a large displacement, and hence it is prompting us to switch over to a nonlinear analysis to get reliable results. So if we click on yes, the software will run it again in nonlinear analysis. Okay, so now that we have our results here, you can see that here we have the same red arrow as we had in our previous analysis. So that is again to indicate that the stress value has crossed the ultimate yield strength and that it is in the nonlinear region. Now that we have had a few examples on static linear and static nonlinear analysis, now we will be switching over to dynamic analysis. And in dynamic analysis, we will specifically looking into how to use 2D simplification. So what is 2D simplification? So it is just an option which can be used to reduce the computational time for models which are symmetric about a particular axis. So before we start, I'll just explain you what we are trying to do here. It's pretty straightforward. We have a die, we have a punch, and we have a sheet metal. So the punch is moving into the die to deform the sheet metal into the required shape. Our main objective here is to check the stress and strain values that are developed in the sheet metal during the punching action. So to get them, we will be required to perform a nonlinear dynamic simulation to get accurate results. So let's go ahead and do that. Let's click on New Study. Here we will be selecting nonlinear. Under that we will be selecting dynamic. Here you can see that by default it is selected as static. So let's go ahead and select dynamic. And here we will be clicking on the use 2D simplification checkbox. And let's go ahead and rename our model. We'll make it as nonlinear punch and click OK. Once you click OK, so the software will ask you to define a plane along which we have symmetry in the model. So for our model, it is symmetric along the front plane. So I'll just go ahead and click on the front plane, and I will select the depth here as 0.015. Here the 0.015 is the thickness up to which we need to replicate the 2D results to get the 3D object. Once we do this, we can see that we have the 3D representation of our model. So I'll just go ahead and press OK. So here you can see that our 3D model has been converted into a 2D. I'll just go ahead and press 7, Control 7. And our first objective here is to apply materials to each one of those parts. Instead of applying material individually to individual parts, I'll just go to parts and hit the apply material to all option. Here I'll select the default alloy steel, hit apply, and I'll hit close. Now we will be fixing the die here. So I'll go to fixtures, select fixed geometry, and I'll select this. I'll select the 3 sides of the die along with the 2 corner edges of the sheet metal. So this is done to ensure that the sheet metal does not slide off once the punching action takes place. So I'll just select them and click on OK. Here you can see the fixed portions of the model with the green arrow marks. Now that we've fixed all the required parts, our next course of action would be to define the direction in which our punch will be moving. So to do that, let's go to Fixtures again, right click on Fixtures and select the Fixed Geometry option. Here expand the Advanced option, and here let's go ahead and select the top portion of the punch. And we're selecting the top portion to define the direction along which the force will be acting here. And here in the front plane, here the reference plane has automatically been selected as the front plane, and here we'll be selecting the long plane direction too. You can notice that the arrow marks here are all upwards, and that's not the direction in which our punch will be moving. To reverse the direction, we'll just click on the reverse direction checkbox, and our punch will be moving for 10 millimeters. So I'll just enter the value. You can see that the direction of the arrow marks has changed to our desired direction. Now below the translation, you can see the variation with time option. So if I click on curve and click on view, you will see how load or transition will vary in this problem. On the x-axis we have the time, and on the y-axis we have the translation. So here we can see that initially at 0 seconds, the translation will be 0 and the die will translate linearly with time. So at 0.5 seconds, the die will move a distance of 5 millimeter, and at the end of 1 second, it will complete the translation of 10 millimeters. The value of translations are negative because the die will be moving in the downwards direction. Now, if we want to change this, there is also an edit option available. Let me just go ahead and select it. Here on the first column we have the time, and on the select second column we can give either load or transition. So currently we have 0 load at 0 second and 1 load at 1 second. Also, instead of user defined, I can change it to unloading type. In this case, the maximum load will be applied at 0 seconds, and then it will be gradually unloaded from the material. And after that we have the loading unloading type of graph. So I'll just press on view so that we can have a much bigger view of it. So here we can see that the load will first increase and hit a peak at around 0.5 seconds, then it will start decreasing. So we can use all these settings based on our requirements. For now, I'll keep the default settings, which is user defined, and I'll click on OK. So when we run the simulation, the punch will be moving down 10 millimeters. So let's go ahead and run the simulation. Okay, I just got an error, so I just reset it and I was trying to find what the error actually was. So I managed to find what it was. I'm not editing it out because this is some small rookie mistake which majority of us make. So I'll just explain it to you. Let's go to reference geometry here and I'll select edit definition. Here, once we scroll down, you can notice that instead of inputting our value in millimeters, we've input into centimeters. So what happens is our die, even though the entire distance is much lesser than 30 millimeters, it was trying to move much far beyond it. So the solver had detected that it is not possible because of the contact sets, that it is not possible for this punch to move beyond the die. So it gave me an error. I was just banging my head and wondering where the error was. So I managed to find it out. So let's change it to millimeters and we will make it into 10 millimeters and select OK. Let's now run our simulation again. Okay, nice. We have our results here. Let's take a look at our results. Since we didn't define proper contacts before running the simulation, we can see that the punch is penetrating the sheet metal and the sheet metal is penetrating the die. So let's go and define proper contacts now. So to do that, we need to right click on component contacts and select contact set. Here we have faces, edges, vertices for set 1, faces, edges, vertices for set 2. So in the blue box, we'll be giving the 3 edges which will touch our sheet metal, and in the target box, we will select the one edge of the sheet metal which will touch the punch. And if you want to give friction, you can just go ahead and select it. Please ignore the stress value, it's just a small visual bug in SolidWorks, just pops up sometimes. And let's select OK. And we also have another contact set remaining, the one between the sheet metal and the die. So let's go ahead and set that. Go to component contacts, right click, select contact set. Here we will be selecting the bottom edge of the sheet metal, and in the target we'll be selecting all the edges which are in contact and which will come in contact. So I'll just go ahead and select all those ones. Again, ensure that you only select the edges and not the faces. If you do select faces, we will end up with a failed simulation. And select OK. Alright. Now that we've set all the required contacts and fixed all the parts properly, let's run the simulation now. So the simulation is complete. Here you can notice that we don't have any unrealistic interpenetrations. And you can also take the look. Here we have three types of results right now. One is the stress, displacement, and the strain. Double click on the displacement. This shows you how much a specific body has moved. For example, if you look at the die, it's all in red. That means it is moved 10 millimeters. And we have the strain and we have the stress. You can also animate the movement. Let's go to displacement, for example. Select right click on the text and select the option animate. Wait for it to generate the frames. And once all the frames are generated, you can just increase the speed, decrease the speed, do whatever you want. You can also save it as an AVI file. To do that, you just need to stop the animation again, hit the save as AVI file, choose a location, and again run it. So it will just compile all the frames and save it into an AVI file separately. I'll just go ahead and cancel it. So if you want to look at the 3D plot of the simulation, you can right click on any of the simulation results and select the show as 3D plot option, and it will generate the same 2D element into a 3D element for us. And we can also get the animation for the 3D die moving up and down the same manner in which we get the animation for this 2D die. And that is how we perform a 2D simplification, nonlinear dynamic analysis on a 3D model. By doing a 2D simplification, we are able to reduce the computational effort required to run the simulation and also get accurate results. Before we end the video, there is one another point that I would like to add here. Along with the material selection, which defines all the material properties, we can also specify a model type to get an accurate output. For example, let me go to the plate example we just did. Let's minimize this and maximize this one, and static. If we consider this plate which is being deformed in this study, this plate is actually behaving like an elastic material. This means that if we remove the force on the plate, then it will move back to its original position, which is not very realistic, as the deformation here is plastic and not elastic. So in order to get a proper output, we have to define a model type which lines up with the material we are using. To provide the correct type of material, we will be required to define it in the materials dialog box. So let's go ahead and do that now. Here, let's right click on any of our models and select apply or edit material. Here in this material dialog box, click on the model type drop down box. Here we will be provided with a list of material types which we can choose depending upon our requirement. Let's discuss what each of them mean and denote. The first and the default option would be linear elastic isotropic. In this option, the material properties are assumed to be constant in all the planes. On loading, the materials will experience deformation and regain its shape back upon unloading without any plastic deformation. The second option is linear elastic orthotropic. In this material type, the user will have to define the material properties along the x and y direction in order to perform the simulation. This is because orthographic materials exhibit different material properties in different directions. Here the material will also revert back to its original position once the loads are removed. While choosing this option, we will have to give the elastic modulus of the material in the y and z directions, along with the Poisson's ratio in all the planes. Since the values are all great, we will have to copy all the values from the tabulation and paste them in the custom materials option to proceed on. The next one is the nonlinear elastic. Here the model is assumed to have non-linear behavior, but the deformations are still elastic. After this, we have plasticity one misses. In this model type, it is assumed that the material's yielding will occur when the one misses stress equals the yield stress of the value. This model is very accurate for ductile materials. Apart from plasticity one misses stress, we have two other models. They are plasticity Tresca and plasticity Drucker-Prager. In plasticity Tresca, it is assumed that the yielding will occur when the shear stress in the model is half the yield stress that is obtained in a simple tension test. In Drucker-Prager model, the yielding is based on the calculations based on the Drucker-Prager yielding criterion. The Tresca and Drucker-Prager models are a bit too complex for a beginner. These two models are developed over the von Mises model and are used only in a few special applications. The next ones are hyperelastic models. Hyperelastic models are used to describe the materials that can undergo large amounts of strain and displacement under small amounts of stress and load. These are generally used to model components made of rubber and other similar materials. The assumption made here is that the material is non-linear, isotropic, and elastic. The next one is viscoelastic. This is used to denote materials which exhibit viscoelasticity. If you're not sure what viscoelasticity is, it is a property of a few materials which can exhibit both viscous and elastic characteristics when undergoing deformations. A good example for this are synthetic polymers, wood, human tissue, as well as metals at very high temperatures. So as we can see, each of these material types can be used to simulate different types of material properties. So before we conclude this video, let's have a quick summary of all the concepts we looked in this video. So we first discussed on how to perform a linear static analysis. We then looked into non-linear static analysis. We also performed a dynamic non-linear simulation. We discussed 2D simplification and talked about contact sets. We then concluded the video with a discussion about different material types that can be assigned in SolidWorks. Well, that's it for this video, guys. We'll meet you again in the next one.